Hey, 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 it's Dr. J. Today we're going to be analyzing graphs using the second derivative. So it turns out the derivative that we spent about a month learning about and exploring all the different avenues is just the first of a whole series of derivatives. Today we're going to focus on what's called the second derivative. So if you have already taken a first derivative, so if you already have the first derivative, then you can differentiate it one more time. And we call that the second derivative, sometimes called double prime. We call this f double prime. This is called the second derivative. It's the second derivative of f, because this is all starting with a function called f. And then there are several notations for this. So suppose you have, I don't know, x to the 8th. You could say f prime of x is 8x to the 7th. That would be the first derivative. And then you could take the derivative of that, 56x to the 6th. That would be called the second derivative. So that's the most common notation, the prime notation. It does require that you have a function, f or g or h or any of the other functional notations. If you don't have a function notation, suppose you have, I don't know, so let me just call this maybe part A. Suppose you don't have a function, you just have something like this, an equation. Well, then you can use what's called the Leibniz notation or the dy dx notation. So this would be the first derivative, 5x to the 4th. Now, the second one is strange the way we write it. I always thought this was kind of weird. We put a squared on the d, and then we put a squared on the x. Don't ask me why. I guess it's you are taking the derivative twice. Oh, sorry. Almost wrote it wrong. The numerator is y, the denominator. You are taking the derivative twice, so the squaring is on the d, and then it's affecting the x variable twice, so that they put another square on the x. The square does not really mean that you're squaring it. It just means that you are doing the operation twice. So that would be 20x to the 3rd for the second derivative, which is what we're interested in today. You have to take the first in order to get to the second. So those are the two most common notations. I know this one's called Leibniz. I think this one's called Laplace or something. They're named after a Frenchman, Laplace, and then Leibniz is a German. Turns out Newton, Isaac Newton, the Englishman that is credited for much of the discovery and the innovation of calculus, his notation didn't survive. It wasn't quite as convenient and easy to write down. You can read it in some of the old texts, but the one that survived through the ages are these two common notations. Let's do some more interesting examples. So suppose we have y equals, or no, f equals 4x to the 6th plus 3x squared, and y equals 4x to the 6th plus 3 squared. Actually, I want to make this one minus, although it really doesn't matter. Just trying to make them look very similar but slightly different. Here are some other notations. You can take df dx. That would be the first derivative. So that would be 24x to the 5th plus 6x. And then when you do it a second time, you say d squared f dx squared. So in other words, this is the same as the dy dx, but we're using the letter f instead of y. I don't use this one too often, but you might see it in a problem in the future. So I just want to show you it. So once you have the first, then you can go to the second. That would be 120x to the 4th plus 6. Running out of room. Here, let's I'm just going to scoot this over a little bit. 24x to the 5th plus 6x. Just so I can have the space back. And then d squared f dx squared is 120x to the 4th plus 6. So that's the f notation. You can also use the y prime notation. Now, this one we do use quite a bit. Typically, we use this to save space, right? And if you're doing a lot of writing in one particular problem, writing df dx squared, all this a bunch of times is messy. And then this one's going to require a little bit of simplification. So first you do the power rule. Like that. And then you do the chain rule. Like that. And then because the chain rule of a difference, you just would subtract nothing. Yeah, because the derivative of 3 is 0. So technically, if I really wanted to show all the steps, it's 6 times 4 is 24, then x to the 5th, and then minus nothing, minus 0. Typically, we don't write that. Now, I like to simplify this by putting the 24 out in front and multiplying it by the 2, and then distributing. And that way, I don't need to use the product rule. You could certainly leave it in the factored form, but then you would have to use the product rule. So it's really a matter of choice. If it seems easier to use the product rule, then leave it in this form and go ahead and go to the second derivative. If it doesn't, and I don't think it does, I'm going to go ahead and distribute it. So 4 times 48 is 172, x to the 11th. 3 times 48 is 144. X to the 5th. I should probably double check my math there. I feel like I'm off a little bit. 48 times 4, 192. I'm so glad I checked. Little thing like that would have screwed me up. I'm pretty confident with that one. That's like an elementary school problem. 48 times 3. It's another way to say 12 times 12. Yeah, 144. So I know it's been a long time since elementary school, but I still have some vague memories of those days. 11 times 192. That's definitely not an elementary school problem, although it is a cool number. 2,112. 2112. 11 times 192. I wish I could remember stuff like that when I see really cool numbers. Sometimes I do. Sometimes I think they're cool and I tell myself, oh, I'm going to remember that, and then I don't remember it. 5 times 144 is 720x to the 4th. So there is your second derivative in two different notations for two very similar but different, similar looking but different results completely, to sort of illustrate the different types of functions that we might be seeing today. I'm keeping today's lesson kind of straightforward. I don't want to get off track. There's a lot of different types of functions in this course, but certainly the most common is the polynomial. So today I'm going to focus on the polynomial. I'm not going to do a lot of other types. Okay, so that is the introduction to the second derivative. Let's do a few more just sort of warm-up problems, and then we'll get into the analyzing or the graphical analysis. And what does the second derivative tell us? I can kind of just, small talk about it as I'm writing down the next question. Well, the first derivative tells you the rate of change, right? So the second derivative tells you the rate of change of the rate of change. So how fast is, or how slow is the change changing? That's a mouthful, but that's what it is. It's telling you the rate at which the rate is changing. So it's a rate of a rate. Now, in physics, we may do some examples. We talked about the origins of calculus and the whole Isaac Newton and the falling apple. The question of interest in that example is how fast is the apple moving, right? Or we call that the velocity, right? The falling object, how fast is it moving? Well, then that would be the first derivative. It tells you sort of instantaneously at any given time how fast that object is falling. A second derivative will tell you the acceleration. In other words, how fast is the apple speeding up, or is it slowing down, or what's happening to the speed, right? We call that the acceleration. I'm not going to do any word problems today, but I just thought I'd mention that as we do the next couple problems. So let's find f double prime of x. So first you got to find f prime. Polynomials are by far the easiest examples to differentiate. It's just the power rule. And constants become 0. And then you can find the second derivative. And there you go. Okay. So what does the second derivative tell you about the graph? It tells you about the shape called concavity. And we're going to do a test to test whether or not the graph is concave up, like the letter U, or whether or not the graph is concave down. Now there are other words for these. When I first learned calculus, I already had a pretty good understanding of concavity. And so if something was concave like a U, we would not use the word up. We would just say it's concave. And then this shape was called convex, right? The reason why we don't do that in mathematics is because it depends on your orientation, right? So if this is concave, this is sometimes called convex, right? And this is what it would be called if everybody stood like this, right? But clearly, not everybody stands like that, especially in mathematics. In the real world, when you're holding an object in your hand, sure, we assume that everybody's standing on the ground. So you can call this concave and you can call this convex. Yeah. The problem is, what if you're standing like this? Yeah. In mathematics, you can do that, right? You can stand on the ceiling. Well, then this would be concave and this would be convex. So that's the reason why we don't use the terms concave and convex. We just say concave down and concave up, right? Because even if you're standing upside down, well, you are standing upside down, and so this shape is still concave down, right? In other words, according to your perception, your eyes, right? This is supposed to be your eyes. So if you were looking at this with your eyes, there's your mouth, it would look like it was concave to you. But because you are hanging from the ceiling, it looks concave, but it's going down. So we call that concave down. Yeah. And then similarly here, if these were your eyes and you were looking at this object and you're standing on the ground, you would also say it's concave. So both of these people are seeing a concave shape, but this person is seeing it concaved up, and this person is upside down, so they're seeing it concave down. So both of them are called concave. So that's the reason why we don't use the word convex. Even if you have a good understanding of what that means, that's not what we're looking for. Okay. So it's concave up at this point. We'll call this point x equals c. If f double prime of c is greater than 0. And it's concave down at x equals c if f double prime of c is less than 0. So these are the two possibilities for what the second derivative tells us. Let's do an example. So f of x is 8x cubed plus 48x squared minus 120x. So let's take the first derivative. We get 24x squared plus 96x minus 120. All right. Let's review the first derivative test. So the first derivative test, I would find the critical values. So let's see, 24x squared plus 96x minus 120. Set this equal to 0. Let's see if we could simplify this. They're all divisible by 24? Yes. So I could pull out the 24. Then I could factor this as x plus 5, x minus 1. So my critical values, the 24 I could just ignore. It doesn't have an x. I would mention, though, if this 24 was 24x, then I would have a third critical value. I'm only going to get critical values from the factors that have x. So remember, it's the opposite of each of these factors. So x plus 5 gives you negative 5. X minus 1 gives you 1. All right. So we have two different critical values. Those are our C's. Okay. So I've got now the second derivative. Oh, by the way, if I do the test for this, let me just do it quickly. I don't want to take too much time. I spent like 2 hours on the last video. Sorry about that, but it was necessary. It's going to go plus, minus, plus. Trust me. I've done this one a million times. Yeah. So at x equals 1 and negative 5, this is what the first derivative test tells me. So these are my x values, right? I got them in order here. Now let's see the second derivative test. So f double prime of x. Take your first derivative and keep going with it. So now I got 48x plus 96. Okay. So watch this. Test these numbers one at a time. I'm going to draw a number line in a second here. So I've got negative 5. You might want to use a calculator. So 48 times negative 5 is negative 240 plus 96. All I care about is the sign. That's less than 0. So that means it's concave down, like this. And so that means that x equals negative 5, there is a maximum at x equals negative 5. You kind of already knew that because this is increasing, positive, and this is decreasing. So the second derivative test is just another way of confirming that this is a maximum value, and it also gives us what's called the concavity. All right. Let's try positive 1. So let me just put that right here. F prime of negative 5 is less than 0. So that's concave down. Let's do F double prime. It's double prime. Double prime of 1 That'd be 48 times 1 plus 96, which is, again, you don't really care what this is. I'm only going to do it once, and then from now on, I'm just going to say whether it's positive or negative. 48 plus 96 is clearly positive. So that's greater than 0. So that's concave up, because f double prime of 1 is greater than 0. Okay, and then in the middle, you have a point x where f double prime of x is equal to 0. This is called the inflection point. So we take the second derivative, and we set it equal to 0. So these are called possible inflection values, PIVs. Possible inflection values. They're kind of like critical values. They're critical values of the second derivative. They're the second derivative's critical values. So this point is x equals -2. So this is called a possible inflection value. Okay. If the concavity changes at this point, or at this value, then it is an inflection point. We call it an inflection point, but it's actually only half of the point. To get the whole point, you would have to plug in that value to figure out what the y value is. So we sometimes refer to this as the inflection point because it points to where the inflection is happening, but it's not the entire point, it's just half of the point, right? Similarly, down here, we call this, a maximum or this one's a maximum and this one's a minimum. But if you actually want the whole answer, you have to take these numbers and plug them back in. Okay. All right. So I guess a summary of all of this. So f of x was 8x cubed plus 48x squared minus 120x. F prime of x was 24x squared plus 96x minus 120. F double prime was 48x plus 96. We have critical values at -5 and 1. We have PIVs. We only have one PIV at x equals -2. You have increasing from -infinity to -5, union 1 to infinity. You have decreasing from -5 to 1. Yeah, that's the first derivative test. The first derivative test told us that. Yeah, that was the plus minus plus. Then we have the second derivative test. Which was negative positive. Now you take these numbers and you test them in the second derivative test. Now you are allowed to pick your own numbers, but you already have critical values. So use the critical values in the second derivative test, and that will tell you that this is a min. Sorry, this is a max. Concave, yeah, concave down. So this is a max. I like to draw the little hump. Concave up. So this is a min. Yeah. And then -2 is a PIV, possible inflection value. So this is an inflection value. It's a possible inflection value until you test it. If it changes from positive to negative or from negative to positive, then it is in fact a inflection value. So it's no longer possible. So we have concave down from -infinity to -2. Concave up from -2 to infinity. And then we have an inflection at x equals -2. I got a lot more to cover today, so I'm not going to figure out the y values. I'll say DIY. Do it yourself if you're interested. If you take -2 and you plug it into the original function, always use the original function to get the y values. And you'll figure out the corresponding y value for the inflection. When I get to the examples that ask for that, I will do it, but this one doesn't ask for that. Okay, let's take some more second derivatives. Without testing them, let's just practice a couple more second derivatives. So example 5. Oh, this one's not f, it's y, but it doesn't matter. It's the same thing. Plus 8x to the 4th. This is about as high as we will go with polynomials. They do go forever, basically, in terms of how large they can become. But there's a limit to how much we're willing to put into this. So that's about our limit for this level of calculus. So let's find the second derivative, y double prime. First, got to find the first derivative. Just march down the line and use the power rule each term. All right. There's no products, there's no quotients, there's no chains. This is about as simple as it gets for term by term differentiation. And then now we can do the second derivative. If you want to mental math, do it mentally, but then check with your calculator. Depends on your level of confidence. I don't need the calculator. I trust it. Yeah. 4 times 45 is 180. 3 times 32 is 96. 2 times 21 is 42. Oh, shoot. Almost messed up a sign, though. Calculator can't help you there. If you're going to mess up a sign. So there's your second derivative. Now, this one's not that easy to test, mainly because in order to do a test, you either have to know what values to test in advance, right? I mean, sometimes I'll tell you what values to test, but not very often. Most of the time, you have to find the critical values, right? And look at how gnarly this is. Remember, to find a critical value or to find a possible inflection value, you have to set it equal to 0, and that would probably take an hour just to do this one problem. So I'm not going to test this one. If you're curious, you can put this into an online graphing calculator and find out what the critical values are that way. But doing it freehand, with a pen or a pencil is not easy. It's not impossible, but it's not easy. And then probably the messiest type of derivative that we will see, the messiest type is a quotient. And I am going to ask you to simplify this at your own risk. So I will say simplify at your own risk. What I mean by that is if you simplify and it's correct, that's great. You learn something. It's an experience. It will benefit you down the road. So it's not like it's a waste of time. However, you might get it wrong and then wish you wouldn't have tried. So simplify at your own risk. I want you to learn. It's going to be important at some point soon. But, it's homework, right? At this point, it's just training. So if you just want to take the derivative and get it right and move on to the next one and not simplify it, you can also do a compromise. You can do a little bit of simplifying to the point where it starts to get messy and then stop. That's what I did with this one. That's what I will do for you today. I will simplify it until I just feel like I don't want to go any farther. All right. So yeah, everybody has their own tolerance. You could get really obsessed with these things and try to spend, an hour on one problem or maybe even longer, All right, let's get into it. So we got a dy dx is the derivative of the top, 18x minus 2, times the bottom, 8x minus 7, minus the derivative of the bottom, 8 times the top, 9x squared minus 2x minus 3, all over the bottom squared. All right. So now here, if you choose to simplify this, which I'm going to, and you get it wrong, then your next step is just a huge waste of time. All right. If you want to just leave it this way because you know it's right, then you can go to the next step. But you know, both of those options have risks. One of them is you could screw up and do it wrong, and then you waste your time. But the other risk of leaving it untouched is it's so messy. Look at this. You got a product rule, you got a constant, you've got a quotient rule, you've got a chain rule, right? So this gets pretty messy. Yeah. All right, so let's go ahead and do simplifying a little bit. So 8 times 18 is 144. That's another way to say 144. Oh, wow. How many different ways to say 144? That's these guys. Negative 7 times 18 is 126. Oh, I forgot my x. Negative 16x, and negative times a negative is a positive 14. So that's that one. And then I got a negative 8, so that's going to be negative 72. 8 times 9. Negative times a negative is a positive 16x. Negative times a positive is a positive 24, all over 8x minus 7 squared. Now let's do some simplifying. The 16s will cancel. The 144 and the negative 72 will combine to just be 72. The negative 126 is all alone in the middle here. And then I've got a positive 14 and a positive 24. So I've got a positive 38. All right, so that is my first derivative. That's my first derivative. Now I'm going to go to the second derivative. Make sure everything's right before we move on to the second derivative. Everything looks good. So now, I'm just going to copy my first derivative down. We've gotten to what I call the bookkeeping part of this course, where keeping good accounting of every calculation. You know, you can make a big mess in your notes or on scratch paper, but then write down the result, like a little tally sheet, and then move on to the next step. All right, so you want to keep good records of everything you're doing. So this is the second derivative now. All right, so the derivative of the top, 144x minus 126, times the bottom, 8x minus 7 squared, minus the derivative of the bottom. That's 2 times 8x minus 7 times 8. Yeah, I've got a chain rule here. Oh no, I'm all out of space here. Let me scooch this over a little bit. So I've got this 8 and this 2. I might as well just write 16. All right. And then I got the top, 72x squared minus 126x plus 38. All over the denominator squared. The denominator is already squared, so I'm squaring the square. So that's going to be a fourth. Trying to save a little bit of room here. Okay, so this is what I mean. It's simplify at your own risk. If you just want to type this in, you certainly can. That is correct. This is the correct answer. I'm going to do one very light simplification. I'm going to write it like this. Watch. I'm going to write it like this. I'm going to cancel the squared here. Turn that into a 1. And then this is 8x minus 7 cubed. And then I'm going to cancel this one entirely. And that's as much as I'm going to do. So in other words, I'm taking my denominator and splitting it up into these guys. So that one becomes a 1. This one becomes a 3. And then that one just disappears completely. Right. And I'm going to do one more thing with the magic of television or magic of YouTube. I'm going to put my minus sign up here. And then I'm only going to write the bottom one time again. That's as much as I'm willing to do today. And again, if you want to go one more step, it's not that bad. You can distribute the negative 16. You can distribute all of these out. But, I mean, this is as good as it's going to get in terms of simplified. It might look nicer at the end. It might have less parentheses, but it means the same thing. So until I actually have a purpose for going any further, I'm going to stop right here. So the purpose now, what is the purpose of all of this? The purpose is to determine concavity and inflection points. All right, so find the first derivative, the second derivative, the critical values, the possible inflection values, intervals of increase or decrease, and intervals of concavity. So concave up or down. All right. All right, so this is sometimes what I call the whole shebang. Everything you need to know about a function, except the actual graph itself, which will come in the next video. So let's just get started with the first derivative. So g prime multiply by 3, so 15x, subtract 1 from the power, 15x squared, multiply by 2, subtract 1 from the power. For a linear term, it's just the coefficient, so 60, and for a constant term, the derivative is just 0. So there you go. So we'll start off with the first derivative and the critical values. So we're going to set 15x squared minus 60x equal to 0. So we set the first derivative equal to 0 for the CVs. You could solve it the way it is, but if you notice that all of the terms have something in common, you could factor that out or divide it out. I prefer factoring. If you divide it, you'll still get the same result. But that number in the front affects the sign test when we get to the first derivative test. In particular, if this leading coefficient was negative, it would be really important. When the leading coefficient is positive, it doesn't change the result, but just for good measure, I'll go ahead and leave it there. In the past, you might have seen me go divide by 15, divide by 15, divide by 15, divide everybody by the same number, and then that reduces the problem. The equation becomes easier to solve. I am essentially doing that. I'm dividing by 15, but I'm just not forgetting that I have that 15 there. Let's try to factor this. If you can't factor it in a minute or two, then it's either unfactorable or you need more practice with factoring, or you're just impatient. I mean, I've been doing this for years and I sometimes give up when I probably could have figured it out. If you can't figure it out in a minute or two, then use the quadratic formula or completing the square or some other method. This is a perfect square, which means that these factors are identical, which means you only have to solve one of them. So our only critical value is x equals 2. We have one critical value. Now, I should also mention this leading coefficient of 15. If that had an x, if it was 15x, then it would produce another critical value, particularly 0. And then when you have identical factors, there's no sense in solving it twice. You get two identical solutions. There's no reason to do that. Just leave it as solving it just once. Okay, so we have one critical value. I'm going to sort of document everything we have up here. So we have a CV x equals 2. That'll be our sort of save for later list. Okay, so now let's do the intervals of increase and decrease. So that's the first derivative test. Now, when you are testing the first derivative, you can test the entire equation, or you can test the factored form. Notice I rewrote it as 15x minus 2 squared because we had two copies of the same factor. So when we're doing our first derivative test, there's only one partition number or one critical value. We're going to test a number to the right, say 3, and a number to the left, let's say 0. Remember, you get to pick your test numbers. You could have also done 1. I always pick 0 whenever it's possible. It's a very easy number to test. All right, so this is the first derivative sign test. Remember, all we care about is the signs. All right, so we're going to plug in 3. 3 minus 2, that's positive. When you square it, it's positive. You multiply it by 15, it's still positive. 0. 0 minus 2, that's negative. Then you square it, positive. Then you multiply it by 15, positive. Yeah. So this means that it is not a max or a min. In other words, it's not an extrema. Or extreme value, yeah. And the function is always increasing. G of x is always increasing. Negative infinity to infinity. Which means the decreasing is dne. It does not exist. All right. Now, I mean, you could say negative infinity to 2 and then union 2 to infinity. But when you union two sets together that have a common number in that point, we usually just include that in the answer. So it's just negative infinity to infinity. But, you know, you could get into the deep philosophy, or what's called the study of argument, where we could just spend all day arguing about whether or not 2 should be included or not. It's really a matter of opinion. You could argue that 2 is neither increasing nor decreasing, in which case you would have to separate them out. Negative infinity to 2, union 2 to infinity, thereby excluding 2. And that is a valid argument. There's a case to be made there. But then you could also argue, well, if it's neither increasing nor decreasing, then that means it could possibly be both. It falls into the sort of middle category. When you draw the graph, you'll see that the answer that I'm giving makes more sense because the shape of the graph is always going to be going up. All right, that's it for that. So we've done first derivative, the test, critical value, and intervals of increase and decrease. And we do not have a max or a min, so no extrema. Or I could just say extreme. All right, let's move on to the second derivative. G double prime, so multiply by 2, subtract 1, so 30x. And then the derivative of negative 60x is just negative 60. And the derivative of the constant is 0, so it's gone. So now we're going to set this equal to 0 to find what are called the PIVs, which is really just another type of critical value. In fact, you know, when I learned this topic 30 years ago, shit, it's been more than that, 35 years ago, maybe even longer. I'm aging myself now. Yeah, 35, maybe almost 40 years ago. I just called everything a critical value. Anytime you set a derivative equal to 0, you just call that a critical value. But now, we've developed a more detailed language, just being more specific. Critical values for the first derivative, possible inflection values, second derivative. Partition numbers are any number that you partition the test. Yeah, they could be any value, including non-existent values like asymptotes and such. This problem doesn't have any asymptotes, so we don't worry about that, but that will be coming later in this lecture. Okay, so hey, what do you know? It's the same critical value. So I got a PIV, possible inflection value at x equals 2. Now, it might very well be an inflection point. I have to test it. Okay, so let's do the test. Now again, for the second derivative test, I'm still 2. I guess I could have reused my last one, but the answers are going to be different, or they possibly could be different, so I'd like to start fresh, although it is the same one. All right. Now, notice that if you plug 2 into d double prime of x, you get 0, right? 30 times 2 minus 60 is 0. That's because it's a possible inflection value, which means you can't determine the concavity at 2, right? It's not an extreme value. So that means the concavity is possibly different. In fact, it is going to be different on each side of 2. So let's test again. Let's test 3 and 0. Same numbers we tested last time. But this time we're putting them into the second derivative. All right, so go ahead, plug in 3. Remember, you don't really care about the result the value of the result, just whether it's positive or negative. So 3 times 30 is 90. 90 minus 60 is positive. 0 times 30 is 0. 0 minus 60 is negative. So this means it's concave down, it's shaped like this. Yeah. And it's concave up, shaped like this. And we will see when we actually draw this graph or something similar to this, that it doesn't quite turn all the way. It's more like this. And that's because the x equals 2 was also a critical value. So whenever a critical value is also an inflection value, then that means it does sort of half a turn, and then right at 2, it turns back up and goes back the other way. These two curves are connected at 2. X equals 2. Again, this is an abstract testing diagram. It gives you an idea of what the shape looks like, but it doesn't really count as a official graph. All right, since it changed concavity from negative to positive, this is no longer a possible inflection value. This is now called an inflection point. At x equals 2. And I do use the word point loosely. Again, technically it's not a point yet. If you wanted to know the coordinates, which we will in probably the future lectures, I would say x equals 2, and then I would go back to the original function, plug it in to figure out the corresponding y value. But I will still call it a point as long as I use the word at. That's the key. I'm telling you where the point is at, but I'm not actually finishing the calculation because that's not the lesson that we're learning today. So that's going to be a lesson for another day. It's also a very easy calculation, but it is time consuming. So for those reasons, I will stop here. So I should also mention that when a critical value is not an extreme, it is neither a max nor a min. Just so that in case it's a multiple choice menu, if that critical value was a max or a min, we call it a local max or a local min, select that. But in this case, you would select neither. All right. I think that does it for this example. Move on to example 8. Another cubic polynomial, 2x cubed minus 36x squared plus 192x minus 3. So find the inflection point. So I want both of them. Ordered pair, which means x and y. All right, and then I want the intervals of concavity. So concave up or down. All right, I'll probably want both, one of each. Although there are functions that are only concave up, and there are other functions that are only concave down, but we've kind of left those behind in the dust. We're moving on to functions that have both types of concavity. All right, let's get right into it then. The derivative is 6x squared minus 72x plus 192. The second derivative is 12x minus 72. I don't need the first derivative test because I'm not asking for increasing and decreasing yet. I'm only asking for concavity and such. All right. So now I'm going to look for the PIV. So solve that thing for x. I'm going to get 6. So that's my PIV, possible inflection value. If it is an inflection point, I have to test it first. Then I already have half of my answer. Right? I've got the x. If it's not an inflection point, then the answer to this would be DNE. You can't give me an ordered pair if it fails the test. All right, so let's go ahead and do the test. Now, since I skipped the first derivative test, you have a choice. You could find the critical values by setting this equal to 0. So you could set this thing equal to 0 and solve it, or you could pick your own. It's up to you. If I am already finding the critical values, like because the problem has already asked me for that, or I've already discovered them, I might do that. Yeah. But if the problem's not, giving me a sort of a lead in to the critical values, and I don't find it necessary to find them, why not just pick my own numbers? Yeah. The only downside to picking your own is you don't know what they are. They're just simply test values. So I want to make that clear. If you pick your own, I'm going to pick 7 and 5. All right. They are not critical values. They might be. I don't know. I just randomly pick them. But there's no guarantee that they're critical. They're just test values. If you use this first derivative test to guide you into these numbers, then you kind of kill 2 birds with 1 stone. You know that there are test values, and they're also critical values, so they give you important information. All right. At some point, I will weave together the 2 concepts and probably have these mega questions, of which we will have less of them when that happens. But I want to get on with this. So we're testing the second derivative only. So we're doing the second deriv test. So it's pretty simple test. Just plug in 7 and tell me whether it's positive or negative. You can do this with mental math or a calculator. 12 times 7 is 84. 84 minus 72 is positive. That's all you care about. So that means it's concave up. All right. Now plug in 5. 12 times 5 is 60. 60 minus 72 is negative. So that means it's concave down. All right. And again, I know I'm repeating myself, but since these were not critical values, I don't know whether they're maxes or mins or not, right? But I wish I did now. I mean, if 7 was a critical value, then I would be killing 2 birds with 1 stone. I would know that it's concave up, and I would know that that's a min. Yeah. And same thing here. If this was a critical value from the first derivative test, then not only would I know it's concave down, but I would also know that that's a maximum. I don't know that. All I know is that it's concave down, and then this is concave up. But what I do know is that this is now an inflection value. Yeah. because it changed its concavity at that point. So, concave up from 6 to infinity, concave down from negative infinity to 6, and I have an inflection, x equals 6. So let's figure out what f of 6 is by plugging in 6 everywhere here. So 6 cubed is 216 times 2. So that's going to be 432. 6 squared is 36 times 36 is 1296. 192 times 6 is 1152, and then minus 3. So 1152 minus 3, then minus 1296. And then plus 432, 285. So this is my inflection point. As an ordered pair. Six and 285. So that's an actual dot on the graph. All right, these aren't too bad when we're only asking for two things, you know. They get a little worse when there's a giant, list of things to do. All right, so now we've done a lot of cubics. I gotta step it up a degree to quartic. F of x is 3x to the 4th plus 44x cubed plus 204x squared plus 288x plus 9. Start with the first derivative. If you're worried that your mental math will be off, I almost guessed 152, but I think it's 132. Then just check it with a calculator. 132. 408 and 288. And then the 9 is constant, so the derivative is just 0. Second derivative, 36x squared plus 264x plus 408. Now you see why I often skip the first derivative test, especially when the degrees are higher than 2 or 3. It's not simple to solve this first derivative always. In fact, quite often it's very difficult to solve the first derivative. So we just kind of mow right through the first derivative and get right to the second derivative. My battery almost died. It tells me this video is going on too long. So we go right to the second derivative and we find our PIVs, our possible inflection values. So solve this for x, set it to 0. Like that. Now look for something that comes out of all of the factors to make it a little bit easier. Usually, I hope it's the first term. Nope, it's not. Bummer. So, huh. Make sure everything is written down right. Then let's go for 12 then. 264 divided by 12. Yep, that works. How about 408 divided by 12? Yeah, that works too. So we'll pull out a 12. And you could divide these all by 12. 22. And 408 divided by 12. 34. All right, so then give this a minute or two to see if you can figure out what the factors are. I'm going to spare you the minute. It's not factorable, but you never know, right? Some of them are very easily factorable. So you've got a couple options. You can use the quadratic formula, or you could do that completing the square method that I've done a couple times. I usually only do completing the square when the leading term is 1. The leading coefficient is 1. When the leading coefficient is something other than 1, just use the quadratic formula. It's a nice exercise in beginning and intermediate level algebra to make sure you still remember your rules. 22, negative 22, then 22 squared, right? So it's negative b plus or minus b squared minus 4a and c all over 2a. Now remember, your a is now 3. You are ignoring this unless it has an x. All right, we've seen some problems in that mega long video I did where the common factor had an x. Well, then I couldn't ignore it. I had to use that as part of my solution. This is a constant. It just pulls out to the front and ignores. All right. It's not going to go away, though. It's just going to be temporarily ignored. All right, so I got negative 22 plus or minus. Again, if you have a fancy calculator, they make calculators now that do all this for you. I'm just using my cell phone because it shows up nicely on the camera. So you get 484 minus 4 times 3 is 12 times 34 is 408 over 6. So that's negative 22 plus or minus the square root of 76. Now, if that came out to be a negative, I would stop. I wouldn't even keep going. I would just say there are no critical, or there are no inflection values. There's no possible inflection values, so there can't be any inflections. But as long as that's positive, keep going. Right? And then we'll round this to the nearest tenth. All right, so just put this in your calculator, round to the nearest tenth. So I've got the square root of 76 is 8.7. And then I'm going to do negative 22 plus that. Divided by 6. So I'm going to get negative 5.1. That's one of them. I've rounded it to 1 decimal. And then the other one, square root of 76 minus 22 divided by 6 is negative 2.2. They're both negative. Okay. Yeah, that makes sense. the square root of 76 is less than 22. So when you add or subtract, you get the two possibilities. They're both going to stay negative because neither one of them was big enough to get up into the positive. So there's two negative. Now, we don't know. These are PIVs, yeah? Possible inflection values. I have to test them, right? If they change concavity, then that means they are genuine inflection values. Right? So let's do the test. F double prime of x is 36x squared plus 264x plus 408. Now remember, when I do the test, it's just like the first derivative test. I can use the original second derivative. Don't use the original function. Or I can use any of the later versions of it. Because this one was so messy, I'm just going to stick with the original. Sometimes the original is cleaner than all of the subsequent versions that come along in your testing process. So I've got negative 5.1 and negative 2.2. Those are my possible inflections. I don't know. I'm going to test them here. Pick some test values. 0 is a very easy one. Yeah, that's greater than negative 2.2. Negative 3 is a nice one in between those. And negative 6. So those are my test values. Right? And since I skipped the first derivative test, I don't have any other candidates, right? So I'm just using them. 0 is an easy one, yeah? When you plug in 0, you're just going to get the last number, which is positive. So that's positive. If you want to gamble, I bet you it goes like that. Right? However, you never know. And I've done 100 of these, and I've had it go 50 times one way and 49 times another way, and then one time it's weird. 1 out of 100 will go plus, 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 or minus, 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 or plus, plus, minus. I mean, any combination of pluses and minuses is possible. So I would actually check by plugging them in here and here and seeing what happens. All you care about is whether it's plus or minus. So let's do negative 3. So negative 3 squared is 9. You might as well just do that in your head. And then 36 times 9. So that's going to be 324. And then you got 264 times negative 3. That's going to be negative 792 plus 408. And remember, all you care about is whether that's negative or positive. So you got 324 minus 792. That's negative 468 plus 408. And that's negative 60. I was right. My bet was right. I bet you this one's also right too. But don't trust me. You never know. These could both be minus. Right? That's why they're called PIVs. They're not guaranteed to actually be inflection values. So let's try negative 6. So that's going to be 36 times 36. Yeah, because I'm just doing the squaring part easily in my head. So that gets one step down the road. So that's 1296. Negative 6 times 264. That's negative 1584 and then plus 408. All right, so I've got 1296 minus 1584. That's negative 288. That's just these two. And then plus 408. I could just stop now. I know that's going to be positive. So I verified that they're all right. So check, check, check. Sometimes you call that guess and check, right? Guess. See how many times you're right. You might feel so confident that you're just, you go, I'm just going to guess every time. I used to do that until I got a few wrong, and I went, oh shit, I'm just going to start testing. And you always get it wrong at the worst possible time when you really can't afford to be wrong. So, I mean, if you're just doing homework, you can be wrong. There's not a big risk in that. All right, so that means that these are both IVs, inflection values. Some people call them IPs, inflection points. They're not really points until you plug them in. I don't want to plug them in today. So I'm just going to say inflection points have X values -5.1 and -2.2. So these are just the X values of the points. They both checked off as being, because they're changing, right? Positive, negative, negative, positive, they're changing. So this one's concave up, this one's concave down, and this one's concave up. So concave up, negative infinity to -5.1, union -2.2 to infinity, concave down, just in between -5.1 and -2.2. Whew! What a lot of work, huh? Let's do a fifth degree very quickly. It's the same process, but you're going to have more changes going on here. So the last example. I really put you guys through it this week, but it just means less for next week. Next week, I'm going to be filming some special videos that show precisely how to draw the graphs. I'm waiting on some more materials to arrive, and I have a studio on campus that I film some graphing videos at. That it's a little bit different format here, so more to come next week on this, but for now, let's just get this one done. So let's just dive right into it. It's actually easier than the last one. It just looks a little more complicated because of the fifth power, but notice it's not a very large polynomial, so it's pretty tame. So we're going to get right into it and take its derivative. And then take its second derivative. The numbers get kind of blown up. Oh, I almost screwed up one of the powers there. And then we want to set this thing equal to 0. You can save yourself a little bit of work by factoring out as much as you possibly can. I always try for the leader. I don't think the leader works this time. But I think 120 will work good. Oh, 120x. They all have an X. 129.60. I hope that works. Yeah, 8. Now, if this has an X, you can't ignore it. You got to solve it. Although it is very easy to solve, you just get 0. Right? Just divide by 120 and you get 0. You only do that if there's an X in that factor. If it was just 120, I just would have ignored it and moved on to this one. Oh God, I'm going to save you the time. This is another quadratic formula, so it's -3 plus or minus. The quadratic formula comes back to haunt us quite a bit. You could just use it right away and say, hey, you know, I know it's coming, so let's just get it over with. I didn't write it, but this is a 3 squared. It's 9. I did it mentally. This is calculus. I'm also going to do all of that in one step. So I've got 8 times 9, right? So 4 times 2 is 8. Oh, sorry. 8 times 8. 4 times 2 is 8. 8 times 8 is 64. Double negative, and then plus 9. So that's going to be 73 over 4. Well, last time it was 76, huh? So I've got 8.5. All right. And then plus -3. And then divided by 4. So that's 1.4. Or, and these are approximations now, 1.38, which is 1.4. The other one, 73 square root plus -3. Oh, shoot, I hit the wrong one. 73 square root negative minus -3 or plus -3 is -11, and then divided by 4 is -2.9. Yeah, it's -2.88. It's 2.9. So these are our PIVs, right? 0, -2.9, and 1.4. All right, now if you just want to guess, you could say concave up, concave down, concave up, concave down, right? That's probably a pretty good guess. You might be right. You got like a 50% chance of being right. But then you have a 50% chance of being wrong as well. And then the other 50% chance breaks up into like 25 and 25. You could be sort of wrong, you know, like one of them's wrong, or the whole darn thing could be wrong. There's like every possibility is there. All right. But I mean, if you really just want to, you know, be brave, you can go, okay, plus, minus, plus, minus. Right? That happens about 50% of the time. Right? But then there's all these other possibilities. I don't want to do that. It's my last example, so let's just get it done. So again, I don't have the first derivative to test, so I'm going to just use my own test values. I'm going to do 2, 1, -1, and -3. You could do it all on the calculator. You've got a good calculator, some fancy ones, you can type the whole formula in and then just put in your X value and it'll tell you what it is. Some computer software does the same thing. Here's what I recommend. Do the powers ahead of time. Yeah. So for example, for 2, I can just do that ahead of time. That's 8. And then I only have to do a little bit of work on my calculator. So that's, so for this one, I'm doing this one. It's 1920 plus a power ahead of time. It's going to be 4. 360 times 4. 1440. And then minus 960 times 2. 1920. Oh, that's a coincidence that these guys match. So that's plus. Yeah. So if you want to guess, I bet you this one's minus. Let's see. Let's put in 1. Oh, do you guys remember the 1 trick from algebra? Whenever you plug 1 into any function, you can just add up all the coefficients. So let's just do this mentally. 240 plus 360, that's 600. 600 minus 960, that's negative. Oh, that saved me a lot of time. -1 has a cool trick too. The odd ones, the odd coefficients, the ones that have an odd power, they change. They change signs. So that's going to be -240. That's going to be positive 960. So keep track of where you're at. -240, positive 960. The evens stay the same. So you have -240, positive 960, and then that one stays 360. So if you want to write that down, you can. -240, positive 960, and then the 360 stays the same. That's going to be positive. This last one, it's going to be negative. I already know it. Yeah. I'll tell you why I know it. When you cube the -3, you're going to get -27. Yeah. Times 240. Just do that one number. -27 times 240. You're at -6,480. Someday we're going to be talking about this in a business context. That's going to mean that you are in the hole. You are -$6,480. And then these things are going to be increasing, right? But they're not going to be increasing enough to get you out of the hole. If you think of this as like a revenue or a profit cost kind of model, right? So if you had 9 times 360, that gets you halfway there. Yeah. Ah, I spoke too soon. Wow. I don't know anything about money, do I? No, I do. I tried to make a money example and it actually got my brain thinking. This is a negative times a negative. It might get me out of the hole. Let's see. 960 times negative 960 times -3, 2880. Is that enough to get me out of the hole? Oh, almost. 2880. So my instinct was right. I'm still in the hole. So that's these two added together. That's these last two terms. But the first term was so big and negative, -6480. It's negative. I hit the wrong button on my calculator, but I got 3240 plus 2880 and then minus 6480. You believed me. I got close though. It's like, if you think of that as a business math problem, we started off, we were negative $6,480, and then we made back a bunch of money, and we almost made it back to zero, which is really the goal of every good problem, is to try to get back to zero. So that means they are both inflections. They're all three inflections. So inflection at, and again, I'm just going to give you the X values. All right, and then the concavity, concave up, negative 2.9 to 0, union 1.4 to infinity, concave down, negative infinity to negative 2.9, union 0 to 1.4. And that is the second derivative test exhaustively. So next time we'll put it all together. We'll find maximums, minimums, increasing, decreasing. We'll draw some graphs. And then once we have had a good dive into the world of graphing, we'll get back to the business and social science, mathematics of calculus. But until that day comes, I'll have to see you on the internet.